organized by the Society of Spanish Researchers in Denmark. And today we have a great panel of experts in computer science. Computer science is kind of a broad term, and we are actually using the term to, well, we decided to break a little bit in different disciplines, computer science, and in order to illustrate what can do computer science for us and for our society. So we chose some of the best experts in these disciplines here in Denmark, belonging to this association. So they are going to show us what they can do. The first talk is going to be done by Chema. He's at CBS, DTU, computer at the Center for Sequencing Analysis at CBS, DTU. He's an associate professor, and he did his PhD in Spain in the CENIO, which is probably one of the world-leading institutions in cancer research. The next talk is gonna be done by Juan Muñoz, who is an engineer, informatic engineer, and he did the PhD in Barcelona, in the Autonomous University of Barcelona, and he's now currently working in a startup company called Vaavud, which is devoted to develop kind of products to measure the wind speed with the iPhone and smartphones. So he actually worked a lot with huge amounts of data, so he will tell something about it. And lastly, the talk is going to be done by Hector. Hector is currently a postdoc at the University of Copenhagen, and he's doing research in linguistics, which is maybe unknown for most of us. But it's quite cool to see how they analyze features and patterns in text in order to, I don't know, develop translators and a lot of cool applications that linguistics has. And he's actually using a lot of statistical analysis as well. So he definitely needs computers to build his activity. And then I'd like to just introduce our association. We have some goals in this association. So we are basically Spanish researchers doing our activities in Denmark. And one of the main goals is try to help Spanish scientists to establish in Denmark. We can use our network of contacts in order to know who's working on what, and also try to promote what our members are doing here in Denmark. Because for us, it's very important to let the general public know why it's important what we are doing and what they are doing as Spanish scientists in Denmark. And also, we want to boost collaborations between institutions in Spain and Denmark. So that is a very good way to do that. And of course, scientific dissemination of all the activities that the members are doing. And we are also trying to get some of the stories in the press here in Denmark and in Spain. So if some of you think that we have a cool story, or even if you don't think it's that cool, maybe for us it is. So maybe we can boost these stories in the press. And finally, we would like to facilitate the mobility between both countries, because that is very important in order to boost the competitivity in science in both countries. So I'm going to give the word to Chema, the first speaker for in computer science. So just thank you very much for the introduction.
So yeah, my name is José María González-Izarzugaza, Chema, and I'm an associate professor at the Technical University of Denmark, DTU, and I work in the Center for Biological Sequence Analysis. Right? So we are a computational group that is doing bioinformatics, computational biology. So what we do with computational biology is we analyze biological processes using the computers as the tool to understand these processes. Okay? And today, I'm going to show you how we can use computers to understand our DNA and to understand the importance of the mutations that we might have in our DNA for our health or for many other aspects of our life. So if you remember from the high school days, each of the cells in our body, or in the nucleus of each of the cells of our body, we have the chromosomes. And the chromosomes are the DNA packed. Right? So DNA is the molecule where all the genetic information is. Right? So we have genes that are our instructions or our manual of instructions where we define how our proteins should work. And this manual of instructions has 4 letters, A, C, T, and G. So these letters, that they have to be in a particular order in the DNA, might be mutated. So you might have an A here, and suddenly you get a C. Right? And you have, for example, these 2 twins, one got a mutation, and they are different. This one has curly hair, whereas the other one has straight hair. And that's because maybe one of the mutations is changing the protein that is encoded by this gene. So we have a change in the mutation, then it's a change in the protein, the function is slightly different, and then you get a slightly different phenotype. Right? But then the phenotypes might not be only that we look different, right? It might not be that we have different eye color or different color in the hair, or that we have curly hair or straight hair. It might also be important because there are some diseases that are associated to genetic disorders. And also, the way we respond to drugs is different depending on the mutational background that we have. So, for example, imagine that you had this particular woman, she got a cancer, and she comes to the doctor explaining the genetic background that she has. So the doctor can see the genetic background she has. Then the doctor will be able to choose from the number of drugs that there are in the market, those drugs that are more likely to respond to the disease that this particular lady has. This will maximize the effectivity of the drug and will help adjust the dose that the doctor has to administer this lady so that the side effects will be minimized. And we all know the side effects of cancer, right? So adjusting the doses and finding which are the drugs that are more likely to cure this person is important. So how do we do this, right? So we read the DNA and we find the mutations. But the problem is that this is DNA. DNA is a very long sequence of A's, C's, T's, and G's, as we said before, and it has 3 billion bases. So this is 3 to the multiplied by 10 to the power of 9, right? So it's a huge alpha. It's a huge book with a lot of letters. And as you can see here, there are genes and there are mutations. Can you notice them? Of course we cannot, right? The mutations are here. There are 9 mutations that we cannot, as humans, identify easily. But this is very easy for the computer. The computer can compare and can decide where the mutations are. So we have computers. But what kind of computers do we use in computational biology? We can use the laptop, but this is not powerful enough. Right? When we start combining things, then it becomes a little requiring, so we need to use supercomputers. And here in Denmark, at the TU, we have Computerum, which is one of the biggest computers worldwide. So it's the number 121 in the world, which is rather big, especially if you think that not all of these computers are used for biological research. Right? There are a lot of computers in militaries, armies, economics. So this is one of the biggest computers used only for biological research. And it's a big computer. So we have 15,000 CPUs, 96 terabytes of RAM, and 3 petabytes of storage. So this is a huge, huge, huge computer, which is more or less like 10,000 of your regular laptops. And this big computer allows us to either run a lot of jobs in parallel, so have small jobs running all of them in parallel, so the time is short, or we can configure it so that we can run big jobs once at a time. So yeah, how do we do it with NGS? Right? So we have this sequencing these days. We have sequencers, which are machines that are able to take the DNA of people and transform it into light, and then it can be easily translated into the letters in the alphabet, in the book. The problem with this is also that they, in spite of being very, very efficient and being very fast, it produces millions of source sequencing reads. And by source sequencing reads, I mean this. You get a lot of these small fragments of DNA, so the DNA is broken, and we can only read the bases in the ends of this DNA. So we will have like 100 letters to each of the sides. and then they will be separated by something that we call the insert size of between 200 bases and 20,000 bases, right? So this, we will have small fragments of DNA that we know the sequence of, that are separated by a variable distance, but we know the distance, right? So that's very important. So then this big molecule of DNA becomes a puzzle with a lot of pieces. If you can imagine, right? I mean, you have 3 million letters here, and here you have only 100. So you have a lot of pieces that you have to put in place. So how will you solve that? Right? You will do exactly the same as you will do with another puzzle that you can do in real life. You will have a picture that you have to copy, and then you have the pieces that you should try to put in place. Luckily, in biological sciences, we have the reference. So it was published at the very beginning of the century, and so we know for a number of people how does the DNA of these people look. So then, if we know the letters in this in the standard book of instructions of people, then we can one by one start assigning what's the position of each of these sequencing grids that we were seeing before. So we know where to place each of the tiles in the puzzle in position, right? Each of the pieces in the puzzle in position. And once we have that, of course, we can read the sequences, and when there is a difference, we can say, okay, maybe this individual here had a mutation. As you can see here, there is a mutation in the reference. You will expect a T, and suddenly the lady in the picture before had a C. So it has a T to C mutation. But of course, we are all diverse, right? So in worldwide there is a lot of different populations, and each of these populations has a different phenotypic trait. So you can tell different people, you can guess where they are from just by looking at them, right? So they have different phenotypic traits, and these phenotypic traits are encoded by the genome of these people, the genetic background. So what's a mutation for some people, it might not be a mutation for others. Right? So that's why it's important to have our own reference genome at the local level. And at DTU, at CBS, we are working in a project in Denmark, where we are trying to define what's the genetic background of the Danes. So we got 50 families with a genetic background that resembles those of the Danes, so very real Danes. So we got them as families, mother, father, and child, and we sequenced those. And we took only 50 of them because sequencing is expensive, but also because we wanted to spend our money so that we could generate data of really good quality. So we sequenced, repeating each of the sequencing a lot of times, to a maximum of 80 times. And then we wanted also to have different of these separations in the DNA, right? So we will have short reads that will be very close together, and short reads that will be separated with a long distance. And that's important. We will see later on why. So with that, we try to define the genetic background of the Danish population. And we did it. And we published this paper. So we got 10 of the families because it was a pilot project. So we wanted to start humble and say, okay, we only take 10 of these families, so 30 individuals. We sequence them and we analyze what's the conclusions we can take out of the mutations these people have. And we published this paper in Nature Communications earlier this year, right? So at the very beginning of the year. So, what are the conclusions of this study? The first thing that we saw is that when you consider the families, you would expect that this little guy is the son of these two people. It should share the mutations that these people have, right? So if you have a mutation here, it should come from either the dad or the mom, assuming that the dad is that, right? But we check for that, right? But so there are some mutations that we call de novo mutations that you cannot find in any of them. So it's mutations that appear in the child, and we think it's mutations that appear in the child at the moment the sperm was generated. Why the sperm? Because we see that when the father gets older, the number of these mutations increases. Right? And it's like it's not a perfect trend, but you can see there is a trend. So when you have a child at 35, when you are 35 and you have a child, and if you are a man, then you have more chances that your child will get mutations that they come that you don't really inherit from the parents. Yeah, and this is supposed to have some impact in some developmental diseases. Right? But, yeah, fair enough. Conclusion number one. Conclusion number two is that we can provide the catalog of mutations that characterize the genes. Right? So we found a lot of mutations, different kinds of mutations, single point mutations, small insertions, structural variations, that most of them were already known. So we were able to corroborate that the mutations that we find are seen in other Europeans, and that we were doing well what we were doing, but also we were able to find 500,000 new mutations that are unique to the Danes, or unique to individuals in the Danish population. Some of them will be unique to particular individuals, most of them, right? But some of them will also be shared by most of the Danes. So we were able to characterize what makes a Dane a Dane. And also you can explain what kind of consequences these mutations will have, right? Some of the mutations will have no consequences, and others will be better or worse for the proteins that we have. And of course, this has implications in the clinic. But if you think of the mutations that we all have, because we all are all different, right? So we will carry some mutations, and we assume that we are all healthy individuals. And at some point, we will acquire, or hopefully not, but we will acquire a mutation that will lead to disease. This is a case of cancer, right? That you usually have a normal tissue that will have some mutations. Suddenly, you get the driver mutation, as we call it, is the one that is helping the cancer to progress, and then suddenly you get the cancer, right? When this mutation can make the cells start replicating a lot, then they accumulate, forming a tumor, so you get the cancer. So, and we use this analogy, right? The drivers and passengers. Because, drivers are those that are really important guys, right? If you think of school bus, children might misbehave in the bus, but it's not really a safety issue. But if the driver starts to become a little crazy, then you maybe have an issue, right? So characterizing we can characterize the mutations of the genes, and we can identify those mutations that are really important for the disease. So you have, let's say, 1,000 mutations. Maybe you can say, okay, these 900 mutations are common to the genes. Don't focus on those. But you have another 100 mutations that might be interesting. So maybe it's better to focus on those and try to identify those that are causing the disease, right? Because we are looking for ways of giving better treatment to the patients, right? So we can characterize the frequencies and we can characterize the mutations, but why not generate a reference genome, right? So a reference that everyone can use to compare against, right? Not only the mutations, but just the stretch of DNA or the sequence of the DNA, and then creating this sequence. And that's exactly what we are doing now, right? So we got 50 years, so we have the 150 individuals, we got the sequencing, and we are trying to de novo assemble the genome. This is a very big buzzword these days, but what it means is that we are trying to put the pieces together without using the reference genome. So we don't have an image that we want to copy. Now we want to just put the pieces as if you were doing a puzzle, just checking which of those really match together, right? So we get the sequencing reads, and we see that the ends overlap. So then you can make the pieces longer, right? But then also you have another trick, and it's these spaces in between the reads we were talking about. If you have very long distances, you might correlate pieces that come together, right? So you know that this piece is here and is in this group of sequence of reads, and this other piece that is connected belongs to this other group of reads. So you know that these two groups are separated, for example, 10,000 bases. So you can order the context, as we call it, right? The groups of overlapping reads. And of course, this is extremely computationally expensive. We need very, very big computers. So computer is a machine for this, right? So that we are using it. And at the end of the day, what you get is the sequence of the DNA of the Danish. So we have a reference genome. This is useful, right? Because if we come back to the slides at the very beginning, where we had here the reference genome, international people, so there would be mutations that belong to the common population, but they don't really belong to the Danes, right? So if you check here in this position, that before it was a mutation because it was a difference between the reference genome and the Danish baby that we were analyzing. There was a mutation here, but now there is no mutation anymore because the Danish genome has also a C here. So maybe this position, the genome, is not that important. Maybe we shouldn't focus on this one. There should be another mutation somewhere else in the genome that is the one causing the disease. So having a reference genome that is private to the Danes will help the Danish society a lot, right? So Danish patients would be able to get treatment of their diseases using a genome that really matches the genetic background, and all the filtering and all the efforts that the doctors might put into helping them are going to be more efficient, and they will get much better treatment. So we get closer to personalized medicine or to stratified medicine just by investing in science and using computers to identify what's encoded in our genes. And that's our group. That's the Integrative Systems Biology group at the CBS. So we do a lot of science, but we also have a lot of fun as well, right? So thanks a lot, and I'm ready to take any questions.
Really cool stuff. Thank you. Where is this reference genome coming from? Not the Danish one, the one that was published in
Science and in Nature.
Science.
Yeah, it's a pull-up of different individuals. So it's a mix, and they have
has to be very, very, how do you say, variada.
diverse.
Yes,
yeah.
diverse.
That's the problem, right? I mean, they are. It will always be biased to the population that gave rise to the genome, right? So they are trying now to have not only a single reference genome. Now there are projects like 1,000 genomes where you get the genome of 1,000 people, and then you get better information about the mutations that they have, better information about the minor allele frequencies. But still, you need to compare to a single genome. Otherwise, all these algorithms will not work properly. It will be more difficult to make them work. So you have to choose something in between. That's why it's important to have something to compare that is the closest to what you are comparing against, so that you see the differences. For example, if you think of cancer, usually you compare healthy tissue or normal tissue with cancer tissue. And then you identify the mutations by subtracting, right? So that's the closest you can get. You're comparing against your own, then you get only the few mutations of that.
And one short question. Do you think pharmaceutical companies use this kind of information to develop new drugs or to at least identify targets? Because I think it's a very big deal for biologists right now in a pharmaceutical company to try to identify a target that will generate a disease or whatever. Do you think they use this kind of information? So do you collaborate with some company, pharmaceutical company? I mean, because I think you're right that the doctor is at the end who will help the patient to give the right medicine, but I mean the companies will have to make.
Yeah, right? Exactly, and that's actually encoded in this picture here. Because when you say personalized medicine, people think that there will be a pharmaceutical company that will generate the drug for you, but they are not that generous.
No, I know.
Then the trick is,
it would be impossible.
It would be impossible as well, but it's more expensive, right? Because the limiting factor is money, right?
I mean, and time.
And time, and your work.
Yes.
But you can choose from the different drugs that you have in the market. You can choose those that are more likely going to help you, and those that are more likely not going to help you, so that you don't use them, so that you don't have the side effects. And you can define the dose, and you can play around with a lot of factors.
But it would be just for chance. I mean, it would be totally random, right?
What do you mean?
Like meaning that the pharmaceutical company will, his goal wasn't made that drug for this population.
No, exactly. But yeah, at least for
But
some,
at least you can
for some you will
target
say,
that.
okay, don't use this drug because you are not gonna get cured. at
Or
all.
maybe in the future
And
they
then-
start preparing those
Yeah,
for different
yeah.
kinds.
So
Yeah.
yeah, and then that links with my previous question. So do you think they use this kind of information?
Actually, there is a lot of research in the HLA regions, it's immunological regions, and that comes directly from sequencing in some cases. It's a very difficult region to sequence because it's very polymorphic, so it's very difficult to put together, so to speak. But once you get that, you have a lot of information of this particular patient, right? Because it's all what leads to transport rejection and all these things. So it's,
Thank you.
So it has been already years since we were told that soon we will have genomes for $1,000.
Yeah.
If Research Hospitality decides today for this one patient we need his genome, how much will it cost and how much time will it take today?
yeah, I mean, I think I don't know all the prices, right? Because I'm not the one in charge of that, but they are getting closer to the $1,000. Of course, if you don't count in these $1,000, you count the price of the laboratory reagents. You don't pay for the analysis of this genome, right? Which is a huge load of work. But yeah, so we are getting close to that, and I guess soon. I mean, soon in Windows time or in politicians time. It's yeah.
One last question. Do you know if is there any initiative similar in Spain, or are we close to any similar initiative in Spain?
Yeah. no, that I know. Not that I know. There are some other efforts in Europe. There is the genome of the Netherlands. There is in Greenland, in Iceland. Sorry, in Iceland, they have something similar. But no, I don't think there is a similar approach coming from Spain. It's a big project. Yeah, maybe it's not the time. Yeah.
Regarding that question about Spain, do you think, for example, Denmark is a really small country, meaning that maybe people is more similar between them. Do you think, for example, Spain, which is a big country as compared to Denmark, would be there real difference between people from the north and people from the south? I mean, genetically talking about. No,
but it's a very quick question. I mean,
are you asking about?
Yeah.
Yes. The guy from Barcelona asked me last.
No. I mean, not entering into politics. There are differences, right? Because it depends on how the populations evolve and where do we come from and all these things. But yeah, I mean, there are.
Because my question is more regarding does it make sense to do it within countries?
Yes, it does.
It does.
Yeah. You need to know what you are analyzing, right? And you need to know, because one of the first things you do is you do a PCR, right? The principal component analysis, sorry, not the PCR, principal component analysis, and then you see the SNPs of these people, and you see that they will form clusters, right? So you will see these people. I mean, you sequence, I don't know, 1 million, right? Some will be from the Basque Country, some will be from some will be from other regions, right? Whatever. And then, if they are divergent enough, you will be able to see that in a PCR. As you can see that there are differences in between Germany, Sweden, and Denmark, for example. So, yeah, why not? And then, if you want, you can go in detail and say, okay, let's.
Individual population.
Yeah, exactly. You can assemble the individual population. I mean, this requires a lot of effort. It's like ideally, right? But that's.
That's actually a question on the same line, and I'm guessing you're controlling for genotypes. So I guess everyone you were analyzing came from a long history of Jensens and Hansens, and they were like super blonde and super white.
Yeah.
But contemporary Denmark is not super blonde and super white. Do you have is there an intention to expand the project for like representatives of sort of the new genotypes of contemporary Denmark?
Of course, when with time, I mean, we will include more and more genomes, right? And this will, we will be able to have, maybe you will have clusters of people, right? And then you will have the genome of the Danes with a certain ancestry, the genome of the Danes with another ancestry, and or you can, all the crossovers as well. So it's but time will tell, right? But for now, you have to start with a very uniform population. So it's yeah.
Any other question? Maybe, yeah.
Maybe I misunderstood, but I think you said that there are 1,000 SNPs that are different in the things that in the other countries. Is that right?
No, it was an example. Yeah, it was
Okay,
an example. There are 500,000 different SNPs that we find in the individual. So it's not.
I was thinking that was very, very low.
No, it's a lot of 500,000 SNPs.
Okay. Maybe we should move on. Yeah. Next.
Thanks.
Next.
Well, thank you very much for staying here. Well, first of all, before starting the presentation, I would like to ask you some questions. Yeah, certification. Yeah. Actually, it's nice because it can be related with the presentation. Where's the mouse? Okay, first question is how many of you were using yesterday as 24 hours as social network? So everybody. Okay, we have two that were using the social network yesterday. Great. And second question is how many of you post a picture or a video or a song, let's say Facebook, yesterday? Okay, we have 3. Well, and the rest were just posting a message. Just to know about, just to talk about the amount of data we are just generating every day. As Eric Smith, the CEO of Google, in August of 2010, he said that every 2 days we create as much information as we did up to 2003. Yeah, that's hot data. Which means you are generating every day a lot of data. And then this data can be just pictures, videos, messages, or just me running and tracking while I'm running. What we're talking about these videos, music, information tracking is what we call the digital trace. So every day we are just generating our digital trace. And all these big companies, they know what we are doing every day. As we see in this graph, is just a graph generated in the Sony Ericsson Mobility Report 2014, which shows the amount of information we generate, meaning that the mobile traffic in 2013, 2012, 11, and 10. And all of these lines represents the amount of traffic we will generate in the following years. As you see, every year we are generating more and more and more information. And you see the line is quite exponential in that 2013, we're generating like 100, maybe just jump to another scale of next to exabytes, a lot of information. So all of this information is like we call the big data thing. How many of you have you heard about this big data thing? 1, 2, 3. Okay, quite a lot. So what is the big data? The big data is just a broad term. It's nothing else. It's just to say that you have a lot of data, which is really complex, and it can be processed through the traditional data algorithms we were working before. To characterize the big data, we have these 4 B's. We call this, the first is the volume, meaning that we have a huge amount of data. It's variety because, as we asked before, pictures, tracking, videos, music, just a post on Facebook and Twitter. That's data, but it's a different kind of data. It has to be analyzed in different ways. Velocity, as we saw in the first graph, the amount of data we're generating in just every day is increasing really, really fast. So the data is generated really, really fast. Now, actually, Dario is taking a picture of me, and maybe will be posted in a social network at some point. So we are generating data. Now we are just generating data because we are in the late stream. And the last one, which is kind of controversial because not all of the big data researchers are saying that has to be veracity in the data, meaning that as the data quality has to be like we can trust in this data, meaning that it can corrupt the data when we analyze it. So some of the researchers in big data, they say that it has veracity in the data, has to be a certain quality. I said that before we were using the data techniques. We cannot use these techniques right now to analyze the big data. And this previous data is what we call the small data. Just following the analogy between big data and small data. The small data, I would like to answer just one question. And the big data is just not a question, it's just a flexible one. For example, the small data has to be structured, meaning that we know where the data is coming from, it's the control gateway. And on the other hand, the big data is unstructured, meaning that we don't know where this data is coming from. For small data, we have organized storage, meaning that this field goes to this place and this field to this place. But for the big data, we don't have this kind of organizations. So we need to use something that's called introspection, which means that, okay, we are just take this tweet and we're going to read the sentence, we're going to click on the video, we're going to analyze the video, we're going to start features of the video, we're going to see the text of the video. This is what is called introspection. Something very interesting about the big data is it's not repeatable. You do an experiment or the big data, and this is the result. And you can do the same experiment with the same parameters, and the result will be another one. While in the small data, always will be the same result. Another characteristic of the small data is that you can just take the whole set and we can analyze the whole set. While in the big data, we cannot. We have to do it in incremental steps because the amount of data is really big. Well, we said that the big data is just a set of tools to analyze this huge amount of data we have. And these are the most common tools we have in the big data, which is data mining, which is more or less what he was explaining, Chema was explaining in the first talk. We have the natural language processing, we'd like to explain in the following talk. We have the ontologies and semantics, which is something I was working before. And the ontology and semantics means that, okay, we have a lot of data, but the computer only understands, well, what does it mean a 1, what does it mean a 0? But it doesn't understand anything else. What it's doing in ontologies and semantics is just provide a semantic definition to an object. Let's say, if you're asking to a computer what's a horse, he will answer it's a word, that's it. But for us, a horse is a word, but it as well is an animal. It's a way to transport. So it has different meanings. And with ontologies, we can just characterize each object with different meanings. Introspection is what I talked before. It's like, okay, we just go from bottom up to top down. The interoperability is the tool is really interesting. I was working as well in another project where we use interoperability. Interoperability is just a tool to, as the word saying that we have two different systems that they are working completely different, and we would like to make it work together. For example, I was working on a project that we have different kind of data for the different policies of the different countries. And the databases of the different policies are completely different, but they would like to interact between them. That was the interoperability task. And another tool that they were using in this genomic algorithms is the data reduction, is the principal component analysis. It's the most common one. We have a lot of variables, a multidimensional space. I would like to reduce this space to just 3 variables because we can just find the expression. And who's collecting the data? That's the good question. We can just collect data while we're doing an activity. We are just surfing on the internet. We're just checking the newspaper. We're checking just a shop. While we are navigating, we're collecting cookies. And we're using these cookies for advertisement. Have you ever happened that you're going just to visit a random company, and then you visit the newspaper, and then you see an advertisement of that company? That's what the big data does with all this data awareness. The music is the amazing world of music. It's a huge industry. What they are doing is just, they are analyzing, they are profiling us. So I'm just listening to Spotify, and they say, okay, this guy likes Metallica, this guy likes Iron Maiden, Ludovic, okay. This guy loves this kind of music. And then this guy loves this other kind of music. But in the end, they are profiling the world to make music that we like that music. That's why Katy Perry, Justin Bieber, all this kind of music, they sounds really similar. Because that's what they are doing with this big data. Kindle. I was really surprised last week when I read an article about Kindle. While you're reading in your Kindle, because I mean, there are other ebooks, but everybody has a Kindle. You have this nice feature that I would like to remember this sentence from this book. Okay, they are collecting all the data. And they are using this data just to make ebooks. That's why Ken Follett has a different book every month. And the last is just what Visa and MasterCard is doing. They are just tracking the things we're buying. Another one is just conversation data, which Hector will talk about a little bit about this. No, not really? Okay, so we'll talk about it. What they are doing with this conversation data is they're just reading our conversation, but instead of being a guy reading our conversation, it's just a machine. But they are reading the conversation in order to just provide more advertisement. And just to know what we would like to buy, what we would like to have, what are our interests. And this way, for example, you remember WhatsApp, Facebook bought WhatsApp like 3 years ago or 2 years ago, I don't remember, and they paid $6 billion for WhatsApp. And everyone was like, why? Because WhatsApp, there's no business plan in WhatsApp. You're not paying, you're just paying $1 per 1 year. Okay, they have like 100 million users, okay, meaning that it's $100 million dollars per year. But they have to pay a lot of people. There are a lot of people working on WhatsApp. So why WhatsApp cost $6 billion? Because of the data. That's the business model. What else we have? Instagram, Facebook, Twitter, Google+, YouTube. This is photo and video collecting. And one of the most scariest things is that this is CCTV. For example, if you are in London, there are a lot of cameras around the city. They are tracking us. They know where we are. Well, let's talk about the use case and then see how that big data works. Well, let's say we have this company called NetMovie with a red logo. And what they're doing is just providing us streaming films. But they have a problem. I'm the product manager. I would like to improve the user engagement and the user experience. So then I'm just setting a goal, which is that improve the user engagement. And then for that, what I do is just monitoring the user. What I'm monitoring, just monitoring what kind of movies he saw, time usage, this is morning, it's afternoon, it's in the night. The user behavior is watching the entire movie, or he stops in the middle, or he stops 3 times, or he's watching the movie just 3 times, just at some point just get bored and then stop the movie and choose another one. They are tracking all of these things. Why they are tracking all of these things? Just to make a better film suggestion. For example, with all of these data I said before, they can track, okay, we have a set of males between 20 and 30 years that on Saturdays in Denmark between 20 and 12 o'clock, they were just seeing a kind of movies. And we have the same profile for females. And the result is completely different. Meaning that if it's a man alone at home, it's around these hours is when I watch for sure an action movie. But if it's a girl, let's see who's gonna choose. She's gonna choose a terror movie, or a drama, or a romantic movie. Meaning that the suggestions they are showing in this net movie software are designed for the specific people in a range, in a country, sex, and time. This is just an example. Maybe they are doing more crazy things. But I would like to show with this example is how powerful is this profiling. Because as a net movie user, I'm really happy to see that they are suggesting movies that I would like to see. But on the other hand, it's really scary because they know how I think. But who else is collecting data? Just not so many years ago, there's a new thing called Internet of Things. What's the Internet of Things? The Internet of Things is just all the sensors we have around the world connected to Internet. They are as well profiling us. For example, we have a clock that is set at 7 in the morning to wake up because I have to go to work. But because it's connected to Internet, it can track the traffic. And if it's rush hour and there's a lot of traffic, instead of being at 7 o'clock, it's going to be 6:30. Not to go late to the office. And what are we doing in our company? What are we doing in our company is something called Internet of Things as well, but it's not so scary. We are not tracking anyone. What we are doing is just, in the beginning, we started doing hardware. We were doing anemometers for smartphones. And you can just go to the beach with your smartphone, your anemometer, plug it into the smartphone, and then check. And after that, your measurement is sent to our server, and we're just showing the information in a map, and everybody, I would like to go to the kite surf. Okay, let's check the map. Okay, I have to go to Lama Strand. Great. But that's not enough, because the business model has to be something related with data. You cannot just show the data. So what we're going to do in our company is just to do accurate weather forecast for a specific area. Meaning that I'm in Lama Strand, but I would like to do kite surf. But maybe in 2 hours it's raining. So as a user, as a person, I would like to do kite surf. I would like to know if it's going to be 10 minutes or 2 hours of fun. So what our company is going to do is going to use all of this data provided by the sensors in the phone, provided by the anemometer we're using, provided by other people's sensors around the world, just to predict that's going to be the forecast for this specific area. As I said before, there's a business. Big data is just business. And it speaks for every business. So whatever you can think about the company, they were using at some point big data. For example, to have a better understanding of the target customers. Social media, there are huge companies here in Denmark regarding working with social media. Text analytics, well, that Hector does. Sensor data is what we do. That's another thing that's kind of interesting. It is the business process optimization. It's just stock predictive models. So do we have to buy more of this product to have this amount of stock in the warehouse? They can also use big data for the supply chain performance, or UPS is using big data for the delivery performance. There's also the sport performance. As I was reading last month, I read that Football Club Barcelona is using video analysis to improve how they play. They're using sensor networks with Cristiano Ronaldo. I don't know if this was a video on YouTube while they are just tracking the Cristiano Ronaldo body with different sensors just to know how this body works, because it seems it's impressive. I said no. And there's another important thing is the nutrition tracking. How do we eat? What's the best, the optimal amount of food we need to eat in order not to get fat? There's a lot of companies in the States doing that. And a lot of people paying every month to have a nutrition plan. To improve health, well, is that what they're doing? They're using big data tools to profile the genome. Lifestyle tracking is what Endomondo does, for example. They are tracking when we are doing sport, but they are offering like other things to improve our lifestyle. And actually, there's another, it's really important, it's just big data is also used, not at all, because they failed with this disease in Africa, Ebola. And they use it to predict epidemic outbreaks. Or maybe they start using after. And here it comes the most important thing about my talk, which are the big data ethical issues. Is privacy there? I would say yes, but we agree with that. Is ethics to earn money based on privacy exploitation? Security, surveillance, and law enforcement. As I talked about, as I said, when you're just going to London, you've been tracked where you're going. Now, most of them, we have these location settings set on, and now someone knows where are we right now. This is big data.
Question: what will be your answer for the second question?
My answer for the second question is yes. No, sorry. My question, my answer is probably not. It's not ethical, but there are a lot of things that are not maybe ethical. So it's how it is, and you have to play this game or just die. Yeah.
Why do you think it's scary, the fact that they, use this Netflix example to talk about?
Why I think it's scary?
Yes, the fact that they use this data of your taste, and I'm alone at my place and I want to see a romantic movie, so the next day that I'm watching Netflix, they tell me the next romantic movie. So
Yeah.
I mean,
It's okay. I mean,
what
we
I'm
are
saying-
using Netflix because we think that there's no problem.
Yeah.
But in the end, they are earning money with our profile, and we are paying for it.
Yeah, but I mean, I understand, but these are fair about my privacy, and I mean, sometimes it's just a fact of ignorance that you have your GPS in your phone activated and you don't even know that it's activated. And you're like, oh, the battery is dead in 2 hours. It's like, come on, you have to desactivate that thing.
Yeah.
So that's the problem. Like, I mean, we should maybe start teaching people how to use the devices, right? And then, no?
Well, I don't think it's
I mean-
it's gonna be like only a tracking thing. But for example, Facebook.
But then don't use Facebook.
Or
I mean,
WhatsApp.
if you're
I didn't
The
know
problem
that.
is that
I'm
even if
using
you
WhatsApp
have-
and I think that it's
even if you
completely
don't have a
private.
smartphone,
Yeah. But I mean, this regarding to this
Yeah.
first question, is privacy there? I mean, it is if you want.
now, for example, if you're in a state, you don't have privacy. If you're living in a state.
No, but
Because of
you
the
can
law.
still live in the stone era and don't have a
No.
smartphone, don't have
At some
internet in
point,
your
at some point, you
place,
need to
and be like
communicate.
you, like, you know, this.
At some point, the problem is that at some point, I mean, I agree with you.
Yeah.
But at some point, you need to communicate with someone. You
Yeah,
have to
you
go
use
to
your-
hospital.
But you use your fixed phone.
Yeah, but the fixed phone in the States, they are tracking all the conversations, the voice conversation.
Don't go to the US then.
But they're gonna do the same in Europe
Yeah. Okay.
because all of this terrorist stuff.
Yeah.
I don't know if you read this 1984 book, and they talk about this Big Brother, and before Vendetta is the same kind of things. They're gonna play with this terror, and then while they are trapping us with this security and surveillance, we think that we are safer because they are just taking control of us. But in the end, we're just losing our freedom.
Why?
Come
Why?
on.
I mean, I'm with Anna.
Yes.
Why is so scary?
Yes. It's
I
like,
mean, maybe we just have to change the definition of privacy because we are in a different world. But why is so scary that big companies they track us? Why?
why?
Well, there's one thing. It's not only big companies. There's also the relation between companies and governments. Most of us are citizens of Spain. Do any of you know La Ley Mordaza?
Yes.
I rest my case. I think this is enough. There was a very funny case because let's remember most of our citizens are very stupid. Does anyone here speak Basque? Right? Which is the Basque word for "and," the conjunction "and." Exactly. So exactly. What if they did? I think they were tracking people's Twitter, and someone was tweeting in Basque. It turns out the word "and" in Basque is "eta," and the user got an email saying you're being registered by the Guardia Civil because you're doing terrorism events.
But you have to blame the guy who wrote the code.
No, but the problem is stupidity.
I mean, this is because he got it wrong. This is
No,
because the guy
because they
wrote
were
it
using
badly.
because they were using a keyword. But it's
But yes.
The keyword was not the
Don't
optimum,
do that.
might know
but they are
the problem is
tracking
in
your
the code,
conversation.
not in the answer.
No, the problem is the
How
human
many
using the
people in the past country speaking in Basque write the word ETA? Most of them,
Of
right?
course,
So
because
that
that's
is
essential. It's like, yeah, you would use it in every other sentence. The problem is not the technology, the problem is the use we make of it. And the problem is also the interaction between states and governments. I think you should, if you find the matter touching, you should definitely consider the documentary they did in Snowden and how the phone companies that actually had in their contracts that their information was private were actually selling all the track conversations to the government. That's also because there was a
And actually, in the States, they are not selling. It's just by law they have to have
Yeah, exactly.
access.
Yeah.
And some of these big companies, all of the data is going direct to the states, meaning that our data belongs to the United States government.
But I mean, I don't know what's so important. That
Well,
I
it
don't
is
want- I don't
important
want
because
to know.
one day
I
you
mean,
will say,
Mama, I'm okay.
no, but one day you will, no, but
Or
no,
then
but
maybe
one
like
day
an
you will
only
say that.
feature that I sent to my boyfriend. I mean, it's I don't know.
Well, maybe it's you thinking that if someday I'm saying that I think that capitalism doesn't work, I would prefer to live in a communist world.
Really?
No, I'm just giving an example. I'm just giving an example. If
But
I write
my
that,
only complaint.
if I write that in Facebook or in Twitter, and I'm traveling to the States, in the entrance, I'm gonna be trapped.
That's not true.
No, that's true. It's
Yeah.
completely true. It's completely true.
Okay, it's
Okay.
true then. It's true.
Okay.
Meaning that I'm not free because At some point, I said that.
Yeah.
Okay.
But I mean, sorry. What this one said? My only complaint.
I mean, I did that because of.
My only comment is not to put so much fair all of this game. You know, don't say like you are being tracked and this is so bad and it's like it looks like we are so fucking scared in a corner and that's not true. Or at least my point of view is not.
There's a.
Well, there is a big debate on this
privacy
thing. So, okay, last question.
Yeah, no, I would like to give two examples of positive use of big data. One example is related to the Ebola outbreak.
Yeah.
And tracking data from the social media, they were able to predict that there was something happening before actually they could see, or you can follow, or you can track the outbreaks just by people going to, for example, the hospital, saying, okay, I have like these symptoms, then I have explosive diarrhea, I have this or that, fever, blah, blah, blah. Then you can use all this monitoring of the data and say, okay, guys, we have something happening. Maybe a single doctor cannot see that there is an outbreak, and you have it in 5 different hospitals in different places in the city. Boom, you have an outbreak, what's out? That's a positive case of monitoring, right, the data. Another case related to the Ebola outbreak, right? I mean, also we have this, all the use of big data for databases and sharing in public all the research, for example. You can just submit your sequence or your sequence of the bacteria or virus that creates this particular disease, and then you will get a community of people saying, so this is the bacteria that caused the disease, it has been seen here, it's related to this previous outbreak, and we did this to solve it. So there you go, that's the solution for this outbreak. So it's not all, I mean, it's not black and white, obviously, right?
Yeah, exactly. Obviously, what I'm trying to say is we can do a lot of good things with big data, but we are not using it for the good purposes.
I think the cameras are useful, for example.
Well, could be or not.
I mean, for example, like the terrorist attack in Copenhagen, we just had to, there was this big register, I had to go around and see where there was cameras. I don't care if they know where I am, because I'm not doing anything that's illegal. But I'm happy to be recorded if they can trace the root of the guy. If you're not doing anything wrong, I don't care about it.
There's always a balance, of course.
Yeah, maybe
between
doing
the good
that
and the bad.
legislation to control that.
Okay.
But this is just a part of legislation, not a part of don't record these risks.
But maybe the case is that in Spain, we are too afraid of sharing our data. Right here in Denmark, you have a registry of every single time you go to the doctor, and you, for main diseases, right, not just a single visit to the doctor, and that's something that you can ask permission to analyze and to get information from that. If you say that in Spain, they will think, are you crazy?
And you can Google your name and your
the address
is there.
Yeah, exactly.
Your place here.
And taxes and a lot of things that we are not used to share, right? So maybe it's just our Spanish mentality that limits us.
The point is that they are making money with your privacy. That's a secret.
That's good.
But you
At some point.
but you normally accept the conditions and the terms.
But then you don't read it.
Exactly, you don't read, but that's a different.
But they can also raise your interest rate in your mortgage.
Sorry, say that again. Sorry, say that again.
They can also raise the interest of your next mortgage with the same way.
Yeah.
They can help you or they can handle
that.
it.
If they know you have an illness, then probably the insurance will get an interest because they know it's not risk.
Yeah, but this is why I was saying before that maybe the problem is that a lack of legislation or a lack of a law that protects me with the data. But I mean, I think we'll make our point here.
Okay, please let's move on because then we are basically like last speaker and.
Which is work? Can I take a sip?
Yep.
Okay. It's a previous one. Okay. Spoilers. So my topic is ideally less controversial, hopefully, maybe slightly less interesting too. So my topic has the slightly overselling title of From Linguistic Theory to Language Technology. So I work in this field that has at least 3 names, and thereby none, because it's not very well defined. Some people call it computational linguistics, some people call it language technology, some people call it natural language processing. Normally say language technology. Computational linguistics is a bit more academic. The basics is essentially that there is a field of knowledge called linguistics that has sort of as a program or as an objective to perform the scientific study of language, whatever language is. I marked those in gray because all these definitions are conflicting. A language is either a kind of behavior humans show, a cognitive ability, a system of symbols, a communication tool. So here we have the question of language is not really a very well-defined thing, because again, something that has 7 names has none. And science is probably not as well-defined as we believe, but this is not a topic of epistemology. Whatever the case, there's something we call language, however it's defined, but it's kind of interesting. There was this guy called Aristotle, a while ago, he was like, like language, we say things, right? And it seems like these things are not atomic. There's like some subatomic elements of language. Of course, this is probably the subatomic languages, the subatomic properties of ancient Greek, which had syllables, like contemporary language. They had case, like nominative, genitive. Some of you might speak a language that has it, but English doesn't have it anymore, and so on and so on. But he started looking at those things and kind of giving them names, thereby kind of kickstarting the science, because the first state of any science is the casuistics and the nomenclature. This is not a strictly Western phenomenon. We also have like the biggest academic tradition for linguistics actually started simultaneously in India. But anyway, let's warm up. One of sort of the properties of scientific description of a phenomenon is the ability to predict its outcome, right? What we normally call as the replicability of experiments and so on. How do you finish the sequence?
Mancha.
La Mancha, right? En un lugar de la Mancha. Why can you answer to this? Why can you answer to this? Because because you are a Spanish speaker and you have been exposed to this sequence a bunch of times. Most of us have read the Quixote once or no times, but however, we're all able to complete the sequence, right? Because we've been exposed to it. Thereby, we have sort of a prior that for this thing, then this thing comes out. So I guess we're getting the notion of replicability. So for this sequence, which you might have observed before, the children went out to play, right? It's also fairly common construction. It's not in your language, and it's not part of the core of literature of your culture. But it's kind of easy to play, probably. Yeah. What about the second one? What about the circumstances? Given the circumstances, she went for the worst option. Whatever, right? This is way more undefined. So this context is vague, and you probably have not observed it before. So here, essentially, what I'm trying to do is to incorporate the notion of frequency of certain observations without actually speaking of statistics. But since I know that you guys handle things like PCA, I forgot. So what about this question? Imagine that I have a pen, and I have to decide whether I set a dot or a period at the end of these things. He sat there and spoke versus he sat there and said. Are they both sort of candidates for being a finished sentence? No. The first one is, right? What about the second one? What's wrong with it?
I said something.
You say something. So we know that the verb say doesn't only have a subject, but probably the object, the thing you say. So we also have an intuition of syntax, whatever syntax is, that somewhat gets represented in text. So there's this human ability called language that has at least text as some kind of epiphenomenon, some kind of leftover of our linguistic abilities. I'm not going to say that text is a result of language, because it would be like saying that fossils are a result of life. That makes sense. So yeah, this would be kind of follow, and he said something. So essentially, natural language processing or human technology or whatever, human language technology, builds up on this thing that I call the big intuition. If we have observed enough data, going back to the big data issue, we have some knowledge about the relation of words between them. And also going back to the bioinformatic example, if we have sort of a reference, we're also able to recognize things as being, for instance, new or unexpected, or sequences that we have not seen before. So the general principle, and I swear this is the only massive thing that I'm going to show. So if we have a text X and some property Y we want to be able to recognize, essentially the whole research question comes down to this. So what is the conditional probability of the thing that I want to actually classify the text as, given the text that I observe? So what is the probability of play given the sequence the children went out to? So, for instance, this is sort of just very simple examples of technology of the field. Given a document, you can generate a summary. Basically, you just have to have provided a mathematical, a statistical model with documents and their summaries. And in a manner very, 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 very similar to sequencing, just with words instead of bases, you would build some kind of model with a certain error rate, because this is technology and definitely not magic. You will be able to build something that summarizes things. Something very similar that you probably also familiar with, but in a way it's kind of the extreme case of summary, which would be like keyword extraction from a document. If I take a document, any document, say whatever, a novel or anything, and I just get all the words, sort them by frequency of the document, and just get the top words of the document by frequency, do you think that's a good strategy? No, Rodrigo shaking his head. Why?
Yeah,
exactly. You'll have a bunch of grammatical words that have no meaning, that are not keywords. So you essentially need to refine your mathematical models to capture something beyond raw frequency, which is just a very poor indicator. Then you get into conditional probabilities, joint probabilities, reference probabilities over something else, right? So probably the star child of sort of consumer human technology. There's the automatic translation case. It's not exactly my field of expertise, but we'll look at some examples from it. So essentially, if you have a sentence in one language and you have some kind of translation of the other into another language, you can train a system to be able to provide a tentative translation into the target language. Another thing that you will never encounter directly. Do you remember those trees we were doing in high school? Yeah. These things can be calculated automatically. Why would you do that? Because it's actually very useful as some kind of as an internal knowledge representation for other things. If you, for instance, you're trying to summarize a piece of news, and you want to reply to the usual who, what, where, can you see how these things actually map to syntactic functions? And then you have some other things, like for instance, very simple one that, like, you given a certain text, recognize in which language it's written. You probably see it dynamically when you're using a browser. Oh, you are on a website in Danish. Do you want to translate it in Danish? And also things from text to sound, sound to text. There are a bunch of things. Your spam filter. Your spam filter basically is a document to spam, no spam classifier. So essentially, research in this field comes down to something as trivial as this or as complicated as this, which is essentially how to estimate the maximum y, or how to estimate the y that maximizes the relation. So I'm just giving you some examples. Like essentially one example on SMT. SMT stands for Statistical Machine Translation. It's not the only kind of automatic translation there is, but it's the one you are definitely most familiar with, probably with Google. So we have a word like point, which has sort of the most frequent translation as punto. It could also be punta, for instance, right? Point of a pen. But what about this? On a point of order, I'm sure you've experienced this before. Do you have any idea why that happens? Or why do you get this kind of things? So as I was saying before, the systems basically for automatic translation, they get a bunch of text, a gigantic amount of text in one language, and its translation in another language. And they just basically exhaust the combinations of words, of word sequences, and make some kind of predictions. How do you get a lot of text and a lot of translations for those texts? One of the main sources for many, many languages is the European Parliament. The European Parliament has the obligation to release translated proceedings for all the sessions. So, unsurprisingly, maybe one day if you want to try it, Google Translate or any freely available SMT system is definitely going to be trained, at least in some data from the European Parliament, which makes the systems very good at legal text and very bad at almost everything else. So let's remember that point can be at least punto and cuestión, right? And this comes from here. Just like actually just some of the first sentence of one of the releases of the European Parliament. If the House agrees, I shall do as Mrs. Evans suggested, Madam President, on a point of order. So, Señora Presidenta, una cuestión de procedimiento. So the system essentially has been doing things like this. We do know, for instance, that the verb agree, which is one word, actually maps to 3 words in Spanish. To agree is estar de acuerdo. You can also say acordar, but it's stuffy. It's not the most natural translation. So normally you would observe this kind of things. So you can imagine that when the system is getting trained or observing the data is essentially, it's not really exhausting all the possible combinations because it's a gigantic space. But definitely, at least things are at least 3-4 words long. So it does things like this, and it gets things pretty good. Like agree becomes estar de acuerdo very often, right? But then it also looks at things like on a point of order or on a point of, and it becomes distinct. Distinct up there and down there, they are kind of the equivalent of an idiom. They're fairly idiomatic of legal language. And since I know that I've also heard the terms before, since you know that in certain areas of language use, we normally call domain, there's a particular way of using language, or even I think there's a particular way of using words, and there are characteristic word sequences of whatever. Definitely, legal Spanish is not scientific Spanish. It's not colloquial Spanish. It's not the Spanish you have recipes in. So in a way, there are a lot of very different instantiations of the same thing, right? And that's essentially what happens. So essentially, the next time you encounter a phenomenon like this, you should be able to know why. So if you say the houses are large, it will be translated as las casas son grandes, because this problem has been observed before. Google Translate has no idea about feminine, has no idea about plural, has no idea about adjectives. There are some other systems that are grammatically informed, but Google Translate, for instance, works in real time. So it basically gives you the best they can in this kind of speed. There's definitely better automatic translation than the one you get through Google, but you have to pay for it. And it can be slower. But if you say the houses are subterranean, which is something I made up just trying to look for an error, you find las casas son subterráneo, which if it is an adjective because it was maybe a noun in the original text, it's definitely masculine singular, which doesn't match with case. This is very, very common. So wrapping up, I don't really have much more to say. In general, the only thing that I can say without getting into really uncomfortable statistical details is the quality of language knowledge is tied to the data that can be observed. Essentially, if automatic translation works on legal data, it's very difficult that you get natural sounding translations for anything else. The methods we use to calculate the predictions, which is essentially what the core of the research is, essentially model estimation, and how much we can generalize from data. Because with a bit of knowledge, we could have probably have built a system that knew about, say, the gender number of adjectives in Spanish. But then again, it's sort of language-specific tuning, and it goes from what you would call basic research into specific engineering. And that's about it. Thank you.
So what are companies doing with the text, or how they do? How do they use
They're using
language
it against
technology?
you.
Well,
Mhm.
against you.
So what are
How do they
companies
use text as a tool for their activities?
There are actually there are many things that one of the things of this discipline is that there's a certain part that is visible, but like many areas of computer science, it is sort of an iceberg discipline. You only see the visible tip. There are many things in your everyday life that run through sort of text-based communication that have been kind of put together using some kind of language technology. It's very easy to cite Google, because it's one of the biggest sort of users, or one of the biggest companies that make language technology available to the masses. But you also have things like Siri, if you're familiar with it. Siri is that lady inside iPhones that orders restaurants for you. I don't know if there's anything else that I can answer your question.
Because I remember I think we talked about that, but some airlines, for instance, are kind of analyzing the tweeters, let's say.
Yeah.
Not getting privacy stuff, but to see if the airline is being kind of well considered by their customers, or
that's a common thing. There's this thing. I think it's kind of on the periphery of it's at the periphery of computational linguistics, but it's definitely language technology. I actually have a paper on this in a couple weeks, but it's a topic I don't like. Essentially, you have a statement, and you first determine if the statement is neutral or not. So if the diameter of Earth is so and so, which would become like factual, and then you have things like, I really hate this weather, right? And then companies are actually spending a lot of money into getting people to track the reputation of, like, oh wow, I love Coca-Cola, or things like this. Yes, that's actually one of the areas of language technology that has hit big in companies over the recent years. It has some major methodological shortcomings if you're thinking like straight scientific terms in terms of replicability, because there are many of the things we try to predict, and from linguistic data, they have a certain subjectivity to them. So actually, even like things of summarization and so on, you normally need some kind of human intuition that you later try to replicate with your model, and then these things become kind of questionable in their generality, right? That makes sense? Because you also have the bias, but you have the bias in the target category you're trying to model. That's also why essentially sentiment analysis, repetition analysis is a task that is, I think it's basically reached its sort of methodological top. I don't think the task is going to improve very much because they have a limit on the quality of the categories they're trying to do. Yeah, but it's alive and kicking.
I have a follow-up comment to what you said. The talk was amazing, right? But I have another example where we use NLP a lot. It's biology. How many papers do you read a week, right? So if you really process this data, I mean, we have all the collections of papers, right, published every year. When you have the abstract, you have the full text, and you can make associations, and you can say, okay, this protein appears in the abstract with this other protein, hence they will probably interact. Or this mutation is associated with this particular phenotype, hence. So it's NLP is everywhere, although we don't call it NLP, right?
Yeah. But there are actually a lot of areas of contact between our respective disciplines, and there's definitely also, in the big conference, there's always a panel for bioNLP. And also, if we got into the boring mathematical details, some of the models we use are essentially the same, with very different parameters. Yeah.
What do you think Google Translate Google use this European?
Why? Because it's freely available.
Okay, but since it's also available, our chat conversations with our friends.
Yeah.
Why would they use it?
Because they would have to purchase them. It's still a company. They have little constraints.
Okay, because
yeah, but there are. But
one thing is for free and the other one is.
Essentially, it's also the fact that you also have to have some kind of quality guarantee in the data and so on. And
yeah.
I mean, do you have translated conversations with your friends?
Yes.
Loli TQM. No, it's something like there's.
But
a
I
lot-
use emojis.
Oh, but that's emojis. But there is a lot of some very contemporary research on user-generated content. But user-generated content has a lot of particularities.
Yeah.
There's spelling mistakes because it's generated on the fly. It's not edited. That's also why many things just fail if you just take something that you get like if you get a Twitter.
But what about books? That you have to buy the book,
Yeah.
right? No, what
You
I'm
also-
saying,
you
why
al-
don't you use information in books?
I mean,
Contemporary books.
I have no idea how much that you can still a company and have some privacy.
Yeah.
I have no idea on how much data their models are fit on,
Yeah.
but I know for sure they're using your apparel because you always have that. Because you have a guarantee that you can also train models between any language because the odds that you can find text that has been translated between any arbitrary language and another are very low. And sometimes I'm sure you've seen it. If you translate between two languages that are not very common, it's going to first translate to English and then to another one.
That's true.
I remember just to do a test once I just put some text in Catalan and in French, which are really close. I mean, it's well just remove the last letter, but like English words appear. Just basically because they don't have enough text for. But that's not really, again, that's not a research solution. It's basically an engineering solution.
And also you get a much better translation, I think, if you go from Danish to English than if you go from Danish to Spanish.
Yeah.
Right?
Yeah,
I think
that's
that's
hardly surprising. Do you have a guess why?
I'm
Well, languages have very similar syntax. The marks of gender and plurality are softer and they're not as pervasive. Spanish has many more verb forms.
Yeah.
So actually, you're projecting from a small set to a small set instead from a small set to a very large set.
Yeah.
If you deal with language that has case or like Basque or Russian, it always looks very weird.
You translate from Danish to Spanish. Is it actually translating from Danish to Spanish, or is it translating from Danish to English and from English to Spanish?
In Google Translate. Next question. Oh, no. Just take enough text. Just take enough text and see if English words appear.
Don't you think that the translation between languages that are common is also better because you have the option to actually modify the translation? You can say, can you provide a better translation for this? And then you are actually training the machine learning over there.
Yes, but it's not a full active learning setup where you're just retraining their system because their systems they take weeks probably to train because they're gigantic amounts of data. But they have sort of a retraining cycle where they get the feedback and then just curate. But yes, of course. There's also a matter of demographics. Languages that have a lot of speakers have a lot of users, especially if you have the right combination between speakers and GDP. You get high quality technology. That's also not very surprising. Like, I don't know, you probably have much better language technology for Danish that has 6 million speakers than for Malaysian that has about 20. Is the population is probably GDP. Anything else? Thank you.
Okay, thank you. Okay, so well, I suggest that we can just grab a beer downstairs and we can stay here for a while and mingle around. And just one last thing, we will probably organize. Well, we're organizing more activities, and the next one will likely be about beer science, and we are. I think that's very appealing. And we are just, yeah, it's super appealing. No, and we probably will have a collaboration with Carlsberg, so that will be kind of fun. And so we will just advertise it on our social networks and so forth, so just be aware of that. And thank you very much for coming, and I hope that you enjoyed the talk, because it was very good.